Hi, welcome to Module 3 of Lecture 13. This is the last module, Lecture 13, and it covers the last of the topics that are sort of more generally useful for political scientists to know up front rather than later on in their studies. And this topic is the multiple integral. Now, having said that, some of you might be scared now because for a lot of people, integration is one of the harder parts of math. The good news is, going into multiple integration, there's basically nothing more you need to know. Everything you needed to know about integration you learned previously in part 2 of the course. Now all this stuff is just repetition, basically. For multiple integrals, as far as we're concerned, it's going to be just doing the same thing several times in a row. Now let me stop there for a moment and note the importance of the phrase "as far as we're concerned." This might be one of the first topics we're going to cover, but not the last one as we go on in this part of the course, which we are not going to give the complete story behind the topic. We are not going to explain how to do multiple integrals in all their varied glory. Right? There are all different kinds of multiple integrals out there, line and surface and volume and so on, and they have lots of important geometric meanings. They come up a lot in subjects like physics. However, as far as we're concerned, for our purposes, we will pretty much never have to use any of those. So the focus here is going to be on the kind of integrals, the kind of multiple integrals that we are going to have to use. And for these integrals, they have some nice properties. First, notation. First notation. So here was one integral, say from bounds a to b, some function integrated over the variable dx. If you don't remember this notation, go back and look again at the lecture on integrals. So here's a one-dimensional integral. What if there are two dimensions? Well, there's my first dimension. There's my second dimension. Here's my function of two variables. I'm integrating over x and over y. That's it. To do modular integral, you just kind of stack them. They get bigger and bigger and bigger. 3, you could do 3 by adding a third over here. Let's say e to f, and sticking another variable and adding a dz. You could have as many integrals as you wanted. For our purposes, you can do them in any order you want, by and large, with one exception we'll get to in a second. But for our purposes, which is not true in general, but for our purposes, you can integrate in any order you want. You can flip them all you want. So for instance, if I decided the integral over x was easier, I could do that one first. Or I might decide the integral over y is easier, in which case I could do that one first. One way of noting this would be to say, and actually the bounds are different. I should probably put this as CD and AB to make it more similar to the previous one. Okay, so I could do it like this. I could write the DZ out here, and then the CD over here with the DY, and then the AB, and there's F, and there's DX, DY, and DZ. This is one way of writing it to be clear what you're doing. First, you're going to integrate over x, over its bounds, a to b. Then whatever you get there will not have an x in it anymore, because recall the fundamental theorem of calculus is this, and there's no more x. So when I integrate the definite integral over here, there'll be no more x, but I will have a y and a z. Now I integrate over y, I will have no more y or x, but I will have a z. And finally, I integrate over z, I'll have nothing. That's a quick example of this to see how this works. It's a really easy one. X, Y, Z. There's my f. And let's say all the bounds are 0 to 1. Well, 0 to 1. Actually, you know what? I'm going to do a different piece of paper here. A different screen. Okay. So now I have this integral 0 to 1, 0 to 1. Makes it easier to remember which bounds are which. F, Y, Z, dx, not comma, dy, dz, and here f is going to be x, y, z. Well, you do it any order you want to. So I can start with x and get the integral, it should equal the integral 0 to 1, 0 to 1 of the integral from 0 to 1 of x, y, z, dx, dy, and dz. Well, what's this thing? much like for a partial derivative, I'm going to treat the y and the z as a constant in this integral. So they just get pulled out of the integral. It's the integral of x. The integral of x from 0 to 1 is 1/2 x squared. If you remember, the power rule for integrals is you add 1 to the exponent and then pull that new number down, divide by that new number. Evaluated at 0 to 1. Remember that line means evaluated at 1, and then you subtract 0 from it. Sorry, you evaluate it at 1 and then subtract the same function evaluated at 0, because x squared at 1 is 1, x squared at 0 is 0. This thing will equal 1/2. This is very fast, but again, if you don't remember how to do integrals, go back to the question integrals. It'll be good practice, good repetition. The main point of this module is just to remind you, is to show you how to do it, multiple integrals, not to revisit integrals again. So this thing is going to be 1/2. We can pull it out. We get a 1/2 out front, and we get this one, and then the integral from 0 to 1. Now there's no, now the yz is still there, right? We can't pull the yz out because we're integrating over y and z. So we keep the yz in here. And we get dy, dz. What's this thing? We're going to treat the z as a constant. So we have integral of y from 0 to 1, dy. That's again 1/2. We pull the 1/2 out again. The z is a constant, so we pulled that out over here. So we get 0 to 1 z, dz, that's also a 1/2, and we end up with 1/8. Note it did not matter at all what order we did it in. We could have done z first, then gotten the 1/2 that way, and it would all been just fine. So the upshot is, you start in the middle, basically. You integrate out one variable, then you integrate out another variable, and you keep integrating out variables until you have no more variables left. These are for definite integrals. I'm using the example of a definite integral because primarily this is what you'd be using multiple integrals for. I'll go for one example at the end, which that's not true. But in general, that's the case. Okay. So that's a multiple integral. When do you see these most often? You see these most often in the context we talked about this previously, which is for probability and for continuous probability distributions in more than one dimension. So if you, for instance, want to know the CDF of a distribution function in 2 dimensions, we call it the CDF in 1 dimension. Looks like this. Sorry about that little blip. Looks like this. Capital F of x will be the integral from -∞ to x of the PDF f, lowercase f, evaluated at some dummy variable x prime, integrated over that same dummy variable. So this is the PDF, sorry, the CDF, which is the integral of the PDF. If you don't remember this, go back to your the material on probability and the last module in that lecture again. One more time. Okay, so that's the CDF. What if you had more than one variable? Well, for more than one variable, it's basically the same thing. So integral of -∞ to y, integral of -∞ to x, x prime, y prime, dx prime, dy prime. So much as in the previous case, you just have a double integral, this is called, and you just do it in order. And again, for most cases we care about, you can do it in any order you want. You can integrate over x first, x prime first, or y prime first, whatever you want. Let's do a quick example. If you recall, the uniform distribution had a PDF in 1 dimension of this. The uniform distribution here is 0 outside of AB and 1 within AB. In 2 dimensions, you can write a 2-dimensional version in which it is 1 inside A and B in 1 dimension and inside C and D, the range of C and D in a different dimension, and 0 elsewhere. If A and B and C and D are both 0 and 1, respectively, for both cases, you get a square. Right? You would get a little 0, 1, 0, 1, and you'd be 1 inside the square and 0 outside. More generally, you don't need to necessarily get a square, but that's the point. The point is you have a 2-dimensional case. There's a 2-dimensional situation in which you are within some concrete bounds in both dimensions. How do you compute that CDF? Well, -∞ is the lower bound, which is A, because the other stuff from A to -∞ is all 0, so that goes away. I think I switched that one, so it's actually, sorry, not A, C for Y. Not that it matters that much because to change the order. a to x times two constants, and the integral of dx prime dy prime. Now, again, you can do it any order you want, doesn't matter. In fact, the same integral basically. What's the integral of dx prime from a to x? Well, the dx prime, right, is just x prime to the 0th power. The integral of something to the 0th power, you add 1 to the exponent, so you get x to the 1st power, sorry, x prime to the 1st power, divided by 1, so just 1. So this is going to equal x prime evaluated at x and a. So that gets us these two constants. I can do both integrals in any order you want. You do the x first, you do the y first, doesn't make a difference. In both cases, you get an x prime evaluated at a and x. That's an x prime, not an x1. And a y prime evaluated at y and c. And that equals x minus a over b minus a times y minus c over d minus c. This is just a two-dimensional version of the same one-dimensional thing we did back when we talked about continuous distributions. Note, if I plug in x equals b and y equals d here, then I get 1 times 1, which equals 1, which is good because that means the chance of being between a and b, the chance that you're less than d in one dimension and less than b in the other dimension is 1, because you have to be less than those two values. You must be between a and b in one dimension and c and d in the other dimension by definition. So the CDF of the function should be 1 at the point where you're at d and at b, and it is. Sorry, at x equals b and y equals d, and it is. So that's good. It checks out. And in general, this is what you have to do with this. Now, I should say in practice, you're rarely going to have to calculate these things yourself. Typically, they get calculated for you in various statistical programs, but it is useful to understand what they're calculating, right? If you don't understand what the program is calculating, you don't really understand what's happening. So this is what it's doing. You have a multiple integral in which you're integrating primarily probability distributions over more than one variable. And you're integrating typically to get a CDF from a PDF. And that's true for most cases you're going to deal with. The one case that's not this exact problem involves expected values and expected utilities over more than one dimension. This can occur, for instance, when your opponent is playing a mixed strategy and therefore randomizing over several actions. If these actions set is continuous, you have a distribution over a continuous set of strategies. If you also have some uncertainty over some continuous state of the world, then you have two continuous random variables you care about. Or there could also be a continuous type of an opponent, in which case you may have 3 continuous random variables you care about. And you might have many opponents, and there might be more than 3. So the point is you can have more than one random variable you care about, in which case you get integrals that look like, say for 2 dimensions, they look like this, in which you're integrating for expected utility over 2 different random variables. And they'll be bounded in over some sets, and so on. So there's other variables that matter here too. But the point is you can basically do the same thing we just did in the previous slide, but now you're integrating not just to get some CDF, but to actually calculate expected value or expected utility of some function. Okay, so that's one way. Note in these cases they're all indefinite integrals. We can also do a situation of a indefinite integral. Well, I can have some function, and I can just not specify bounds. What happens then? I'll end up with some different function plus c, right? So I could call this capital F if I wanted to. And note, x and y would still be in that function because I would not have integrated them away. I'm just integrating the indefinite integral to get the antiderivative, basically, plus some constant. And I'm stepping the constant out to make sure you remember there's a constant here now. But otherwise, it's the same thing. So you can do indefinite integrals the same way you do definite ones. In fact, it's usually easier because you don't have to worry about which integral goes with which bounds, because it's easy to forget, if this is a and b and this is c and d, which one's the one that goes with x, which one's the one that goes with y. You got to keep track of it carefully, right? So I said you can do in either direction you want, but keep in mind if you're going to flip directions, is the c and d attached to the x, or is the c and d attached to the y? Just make sure you're careful about which one you do. If I put it like this, the c and d attached to the x. So if I flip the order of integration, I should also flip the order of boundary to make sure I'm integrating y first and using the right bounds for y in this case. That's almost everything. There's one sole exception to the nice rule that you can flip everything around you want. As far as we're concerned, there are lots of exceptions outside of what we're concerned with, but there's one exception as far as we're concerned, and it is this. If the bounds have the other for one variable have the other variable in them, you must integrate that one with the variable in it first. That's probably way confusing, so let me be very clear here. If, for instance, you had a situation in which these bounds were c and d, and these bounds were a to x, so a to y, and you're integrating f of x dx dy, you must integrate x first. The reason is when you integrate x, the integral will have a y in it. Because you are next going to integrate over y, you must have already gotten the y out of this integral to properly integrate it over y a second afterward. Done this way, you end up with a number. Right? This would be some number, I don't know, c, right? C. This would be some number q, right? An actual number. If I flip the order of integration, to do that first, well then I'll get rid of all the y's here, but then put a y back over here. And that doesn't work. So the one exception to flipping the order any way you want occurs when one of the bounds, one or more of the bounds for one of the integrals contains another variable you are integrating over. This would not be an issue if this were like z, because z can stay around. You're not integrating over z. Z can be in the end product. But no y can be in the end product because you're integrating over it. Therefore, you must integrate all the integrals that involve y's in their bounds first. Typically, you will always end up with at least one integral in these cases in which you have no variables in the bounds. That should be done last. If you have more than one with no variables in the bounds, you can again flip the order any way you want, as far as we're concerned here. But you cannot flip the order willy-nilly if you have a variable in the bounds of one integral that you will then be integrating over later. So here, since we're integrating over y later, we must resolve the integral that involves a y in the bounds first. So let's give one quick example of that before we end this module and lecture. Let's say I had 0 to 1 and then 0 to y of the integral x squared y dx dy. I cannot flip the order. I must complete the integral over x first because the integral over x involves a y. I cannot do the integral over y first, even though the integral of y is a little easier. So the integral of y is just 1/2 y squared. It's slightly easier, very slightly. And it's easier to plug in bounds, 0 and 1. That would be an easier case, right? So doing this integral first would be easier. You would get 1/2 like we did before. However, that's wrong. You cannot do that first because that would remove all the y's from the integrand, and we'd be left with 0 to y x squared over 2 dx, and we'd have a y left over. That's bad. So we can't do that. We must first integrate over x. So we'll treat y as a constant. Pull it out. The integral from 0 to y of x squared dx. Do this one first. The integral of x squared is 1/3 x cubed. So this thing is going to equal 1/3 x cubed evaluated from 0 to y. That at 0 is 0, so you get 1/3 y cubed. So that equals 0 to 1. This thing is 1/3, there's a y there, 1/3 y cubed dy. Now all the y's are now in the integrand, nothing more in the bounds, no more variables in the bounds, we're good to go. This is the integral of 1/3, 0 to 1, y to the 4th dy. Integral of y to the 4th is 1/5 y to the 5th. So we have 1/5 y to the 5th, evaluated at 0 to 1, y to the 5th at 0 is 0, y to the 5th at 1 is 1. So that gives us 1/15. So done properly, integrating over x first to get rid of the y's in the bounds first, enables us to get an actual number, 1/15. That's the answer to this integral. That's it. So you've seen all the relevant stuff here. Again, there's tons more on multiple integrals out there in the world. It just does not come up. They don't come up very often in any kind of social science context. So we generally don't bother learning them right now. Should you encounter them later, you can always go learn them yourself. They're the sort of second half of, they're the other part of Calc 3, a typical Calc 3 class that we're not going to cover in this course. Would be things like volume integrals and surface integrals and line integrals and things like that. Okay, that's it. Thank you very much. In the next lecture, we're going to do sort of the more advanced topics in multivariable calculus that you will need to know, but don't necessarily come up at the very beginning of your training in social science methodology, whereas this stuff comes up pretty quickly. That's it. Thank you very much.